Okay. So the first talk today is going to be on delegating RSA decryption, and Giovanni de Crescenzo is going to give the talk, and hopefully can also list his co-authors so that I don't mispronounce anyone's name.
Thank you very much. Can you hear me?
At home, we hear you.
Okay.
Yes, we can hear you. Sorry, I had to click the Zoom window. There we go.
Wonderful. Thank you very much. So again, my name is Giovanni di Crescenzo. My company name these days is Peloton Labs. We are still in Basking Ridge after many years in New Jersey. My co-authors, Matluba Khodjaeva from CUNY John Jay College of Criminal Justice in New York, Delaram Kahrobaei from CUNY Graduate Center, also in New York, and Vladimir Shpilrain, also from CUNY in New York. Table of contents. So we will go over some introduction and summary, in particular about the problem of delegation, the problem definition and modeling. We'll talk about some of the history and some natural questions that were posed. In particular, we'll talk about the problem of delegating RSA decryption, some negative results, and specifically on the impossibility of client-efficient and exponent-private protocols, and some positive results in the area on the possibility of protocols meeting all but one of the requirements. And we'll finally conclude with lessons learned from a number of failures from the entire literature, actually, and as well as a number of failed attempts when it comes also to these positive results. And essentially, leaving still the problem open, and but at least characterizing the state of the art on the problem, also in light of some of the most recent results, and trying to understand why this problem has been open for so long and then has been so elusive. Let's start with some basic facts and knowledge about the separated cryptography or delegation or outsourcing of cryptographic primitives. So those are the three terms that you might have mostly heard in the literature. The problem was probably posed as early as in 1985 by John Feigenbaum. This is my earliest reference, the earliest reference that I could find. At the same time, only a few years later, there was a first paper by Matsumoto et al., MKI 88, that actually started proposing some protocols for delegating cryptographic operations, and in particular already delegating RSA decryption, which is the problem that we are going to consider here. And we will talk about those protocols as well as future protocols. But before that, the main question that is studied in this area is that of allowing, how can we allow a computationally weaker client to delegate cryptographic computations, generally expressed as a function y equal f of x, where x is the input owned by the client, f is a function that is known by the client and by some computationally superior servers. So why is this problem important? There is a major application domain that is extremely of extreme interest today, and it's the Internet of Things, where we have many different clients. The so-called things are model-less client, which can have very different types of processors, from just slightly weaker than our usual laptop or cell phone to extremely weak computing devices. And so for those reasons, these clients will definitely benefit from delegating computation, as much computation as possible, to more powerful servers, and in particular cryptographic computations. So what is the typical solution to delegation? It's a protocol like in the picture. So between a client and a server, it's an interactive protocol typically one round of interaction, occasionally more. We like to divide that protocol into an offline phase, which is run presumably when the client is deployed, or very rarely. And so it is run in a phase where the client is not computationally restricted. The client is potentially connected to a power source. And then an online phase where the client is presumably, it could be battery operated, for instance. And so that's where the client is computationally restricted, and that's where it's of great interest to the client to delegate as much computation as possible to reduce resource usage, to reduce, in particular, battery consumption, and generally speaking, runtime, which is related to battery consumption. So this is the structure and the syntax in the picture. The requirements are listed on the side. We have result correctness. We wanted if the client and server honestly follow the instructions at the end of the protocol, the client obtains the function f of x. We want input privacy. The client's message should not reveal any information about the input, and that can be modeled both in a simulation-based definition, like in secure multi-party computation, as well as using an indistinguishability-based computation definition. Result security says that even a malicious server should not be able to convince a client to accept a result different than f of x, except for very high probability. And finally, resource efficient. Again, we want the client's runtime to be significantly smaller than the runtime for computing the function without delegation. And then other resources also should be well used, like communication complexity, the client storage complexity, and the runtime of the offline phase. All of those should be minimized. Delegation of RSA decryption. We are all familiar with the RSA functions, which recapping here on the left column, listing both the RSA encryption exponentiation and the RSA decryption exponentiation. For this talk, we mainly focus on RSA decryption exponentiation, but we will be occasionally talking about RSA encryption exponentiation as well, especially large exponent RSA encryption. Not necessarily small exponent. Now, to capture meaningfully distinct input scenarios in delegation, we have definitions for whether these inputs have to stay private or are public, and whether they're available in the offline phase or only in the online phase. And so depending on mixing and matching these notions, we get these labels: public online, public offline, private online, and private offline. And so, for instance, we can say that the RSA encryption is a base private online exponent public offline exponentiation function. But as you see, decryption is different. Decryption is base public online exponent private offline. Now, this apparently small difference is actually critical. It's critical to the point that we do have a delegation protocol for large exponent RSA encryption. We came up with that in 2019, but the delegation protocol for RSA decryption has still remained an unsolved problem. Again, since 1988, and this has had multiple failed approaches in the literature. So this paper, as I said, it will deal especially with delegation of RSA decryption. And we in particular observed that there has been much progress actually in delegation, but the problem of delegating RSA decryption remains particularly elusive. So in particular in the literature, we now have delegation for exponentiation in discrete logarithm groups, where the dominating online computation by the client is a small exponent exponentiation with a very small exponent instead of the exponentiation to the full domain exponent. also a large exponent RSA encryption, also bilinear map pairings, and even modular multiplication. So in rings. So for all of these operations, we have a delegation protocol in the literature, which only requires the client to do some much simpler operation. In the case of exponentiation, it's the reduction of the exponent size from, let's say, 2,000-3,000 to 50, as an example. But even for pairings, we have a similar reduction. We have protocols where the client's simpler operation is a small exponent exponentiation in the pairing group. Still, given all those results, the problem of delegating RSA decryption is still open. Those results don't seem to help as much, or at least this has not been studied enough. So in what follows, we summarize the state of the art on delegated computational RSA decryption. We discuss some potential lower bound results, some potential reasons as to why this problem is still open, and we discuss some of the approaches that have been tried in the literature and where they failed. Okay, so let's start first of all talking about the lower bound results, and these were actually produced by in 2016 by CLV, and they proved in a generic group model, and actually the result was not exactly for the RSA group, but was for prime order groups. So they proved that public online based private offline exponent exponentiation in prime order groups, any delegation protocol for such type of operation will come up with some limitations. And the limitations, they prove multiple theorems, which we captured in this figure that is also in this table that is also in the paper. And that essentially tells you how much, in the second column, you see improvement factor, right? So that's how much you can improve with the client's runtime in a delegation protocol versus the non-delegated computation, which is interpreted here as the square multiplying algorithm for exponentiation, under the assumptions that are on the remaining third, fourth, and fifth column. So in other words, in the third, fourth, and fifth column, we are making assumptions of reasonable efficiency that we satisfy in other delegation protocols. But we see that as we make those assumptions here, there is some kind of a maximum improvement factor. What does that maximum improvement factor mean? It means that if we target a higher improvement factor, then the authors actually prove that there is an algorithm that breaks the privacy of the exponent. So that's a quite interesting result. Again, it's not for it's only for prime order groups. It's not for RSA groups. But assume for a moment that this can be extended for RSA groups. So then the question is, let's look at all of these improvement factor numbers, and can we still come up with non-trivial improvement over non-delegated computation? And so that's what we've been considering. And I mean, of course, the full answer will be, I will show later some protocols. And so one has to compare the gap between the results of the protocol and these barriers that you see here. But I'll give you the spoiler alert right now. So the answer is yes. So there is a significant gap between these lower bounds, these barriers, and what we achieve with the current protocols, that some of which I will show later. And so, yes, there is much room to close that gap in terms of research. And so, so there is opportunity to actually come up with delegation protocol that have some improvement, if not very, very large. Very, very large is not possible by the lower bound, but reasonable, small constants, reasonable constants, it is possible. Okay, so now let's move on to protocols. So the first approach, which was influential, and in fact, it was influential for the entire literature, was that by Matsumoto et al. In 1988. Now, this was the first paper proposing protocols for the delegation of cryptographic protocols. The basic idea was that the client will send some randomized masking of the exponent, the private exponent D to the server. The server will compute exponentiation to exponents that are related to the masking and sends the result to the client. And finally, the client will turn the received exponentiation result into the needed exponentiation. And the specific masking was some kind of a linear combination modulo phi of n, where D was represented as F1 times D1 plus ... Fm times Dm for some random bits F1, Fm, and for some random integers D1 and Dm. These integers were not too large, or typically bounded. Also, in some variants, also the weights of this random vector F kept secret was not too large either. And so this seemed a very interesting approach in that recovering D might seem to require exhaustive search of all possible vectors. But actually, after this paper, there were about 20 papers that were published containing faster attacks to the protocol and all proposing protocol variants and improvements, as well as faster attacks to these variants. And so, so there's no time to do a full literature discussion of those papers, but I'm pointing to two sections that do most of that. And I want to stress as a result, as a conclusion, that there are both active attacks and passive attacks that are much faster than exhaustive search. And so these protocols, unfortunately, this family of protocols, unfortunately, is not currently solving the problem. There were more recent approaches as well. There were at least 6 papers that proposed the protocols where the RSA exponent was hidden in a linear equation that depends on some other random value T in the exponent group. And we analyzed these protocols. They all have very major similarities. And we noted the following properties that essentially imply that the protocols do not simultaneously satisfy input privacy and client resource efficiency. So of these 6 papers, one variant, one of the 6 papers, the variant of this approach used in this reference was actually broken using lattice-based cryptanalysis techniques, and it might be plausible that the other papers also might be subject to this cryptanalysis. But we can prove these 2 properties that basically they either satisfy full input privacy or client resource efficiency. But we do want both properties for these protocols. Another class of techniques was that of exponent masking, where the exponent was masked by a multiple of the group order. Again, the exponent here to be masked is the exponent D of the RSA decryption computation. Also, this would seem a very interesting and valid idea, since on one hand, the random value will mask D, and on the other hand, the server exponentiation to a multiple of the group order will cancel out. And so C, the client will actually recover an exponentiation to the original exponent. However, these protocols were broken also using lattice-based cryptanalysis techniques. Okay, so that's for that's for work by others. We also produced some protocols to aid in helping to solve this problem. So first we observed that result security can be obtained almost for free by using delegation of RSA encryption, and this reduces the problem of just achieving input privacy. When it comes to achieving input privacy, we produce the 2-server protocol, but this protocol does assume the 2 servers do not collude, and it is breakable if the 2 servers collude, so it does break privacy. I have to run a bit because I only have 5 minutes, but so we then produced 2 other protocols, P2 and P3 mentioned in the paper, and we have this table that compares our 2 protocols with 3 other protocols from the only reference really that we found that produces provable protocols in despite not meeting all of the other requirements. And so if you read carefully the table in the paper, you'll see that essentially all of these protocols perform reasonably well in almost all of the requirements. They have good storage complexity on the client. They have a good number of messages, up to 4. They satisfy privacy. Almost all of them, they only require 1 server. And the client computation is significantly reduced over non-delegated computation, but they all have significantly large communication complexity. And there are improvements between the protocols. And so that's where they essentially fail. They use different representations of the secret exponent D, and that requires the client to send many values to the server, or vice versa, the server to send many values to the client in the group. That unfortunately results in reasonably large communication complexity. So that is the metric to improve in these protocols. But otherwise, these protocols satisfy all other requirements. And so I believe I'm close to concluding. So conclusions. So why is delegation of RSA decryption so much harder than for the other operations? Not totally clear yet, but we do have a number of lessons learned. So first of all, it is possible that the lower bounds that were proved for similar problems in prime order groups also apply to such groups. The problems are so similar, and it doesn't feel like the group structure, it will change those lower bounds significantly, although that also has not been proved yet. But even if those lower bounds on efficiency were true, that will still not prevent a positive impact from a delegation solution. So a delegation solution will still help, although perhaps not as much as for the other operations. So we discussed 3 main approaches. We discussed exponent splitting by Matsumoto et al. Splitting the exponent as a sum of inner product between 2 vectors, one of which remains secret. And it turned out that there were attacks that were much faster than exhaustive search. We discussed exponent masking in a linear equation, but that did not simultaneously satisfy client efficiency and input privacy. We discussed exponent masking with a multiple over group order, and that was broken by lattice-based cryptanalysis techniques. Not clear if any of these techniques needs to be thrown away. Perhaps they were just not used well, but the way they were used by many authors unfortunately resulted in all of these attacks. Also, we discussed lesson learned about 3 main approaches that resulted in protocols with that satisfied all properties except for communication efficiency. Those were based on rewriting of the exponent according to a particular representation, but that required either the client or the server to send many group values. So there's still a significant gap between these protocols and what will be still allowed by lower bound results. So the problem is open and has been open for a long time, and I hope what I produced here will help as many people as possible to make progress. And that's my talk.
Do we have any questions in the room for the speaker? Yes, we have a question, so hold on one second.
Hello, thank you very much for the presentation. I have a question about the exponent splitting. So here you compare the attack with exhaustive search, but you talk about RSA. So why do you compare to exhaustive search?
Good question. So the authors, let me see, what is the slide? So the authors proposed this particular, you use this particular equation to split the exponent D into these values. They send, the client will send the values F1, Fm to the server, and will keep secret D1DM. So if you can exhaustive search D1DM, given F1 FM, you can find D. And so the authors that proposed this approach thought that exhaustive search was the best way to violate the privacy and find D. But indeed, there have been better attacks. So you're right that so exhaustive search here would have to be mentioned on top of any attacks that we have on RSA decryption. I guess it was more of a way to say you would have to do exhaustive search to help any attack that you have to find the RSA secret key. So, but yes, there is still the underlying capability of running any of the attacks that we know to the RSA key. But as I said, it turned out that there are actually faster attacks. If you go to these two sections, you'll find some of the references. There are faster attacks than even exhaustive search of this vector of random integers D1DM, sorry, random bits F1 FM to actually find D. So in the end, it was possible by just given the random integers D1DM to find the F1 FM very efficiently and then eventually find D.
Any other questions for the speaker? All right, let's thank our first speaker once again. All right, and I will just